I'm going to blitz through what we did here with objects, right? First, the whole idea was objects, we basically get to define our own type. And it's a way to have data and functionality coupled. And remember, like, you know, we define an object by writing a class, and the class is like a blueprint. And then if we ever wanted to make an instance of that class, we call that the object. When we make instances, well, Python goes and looks at the class definition of what a circle is, and then it makes circle objects. In the same way, there is a list class somewhere, and every time you made a list, Python went and looked at the list class and did what it did based on what was written inside the list class. So we started with a circle. You start the class by just saying class, name of what we want. But remember, there's a convention. Everything in Python, we use snake case. You separate words with underscores. Except when you're making objects, you use camel case, where every word, you don't use an underscore. Instead, you don't leave a space at all. You just start the next word with a capital. So, for example, that would be like something. That's like two words, but see how it's kind of separated. But there's another catch. This is typically your camel case. But when you're defining an object, you always start it with an uppercase as well, like this. So that's the convention. If you don't follow the convention, Python will still do what it's told, but you're breaking the convention and everyone will hate you. So we created the constructor. That was that, they call them magic methods or dunder, which I hate that word. Underscore, underscore, init, underscore, underscore. Be aware, it's init, not int. That typo always gets me. But this is where you define this is where you put any code that needs to be run whenever you make an instance of that object. And the first version of the constructor, we just created this attribute, which is a piece of data associated with that object. And we assigned its value to 0. By default, whenever you create a 0, its radius is 0. And we also saw this self variable here. But this is the implicit argument. So although we write it there, we don't actually include anything here in like the arguments that we give to when we create it. So for example, here is creating two circle objects, but you'll notice I never put an argument in the parentheses, even though the constructor says it needs one. That's the implicit one. You just ignore it. Here we were changing the radius values of them to 1 and 5. But then we went and we're like, well, let's add a little bit to the constructor. We added a parameter to the constructor, radius. Again, it looks like there's 2, but really there's only 1 because the first one's that implicit one. So we give it a value, and then instead of by default, whenever you create a circle object, its radius is 0, well now instead, by doing it like this, with this parameter, when you give it an argument here upon creation, it sets its radius accordingly. And then we added functionality. But what did we call functions inside the class? Uh-oh, come on. It's literally, oh boy. Yeah, methods, of course, they're methods. It literally says it right there. There you go. So here's an example of one. Notice that the constructor is not shown for brevity. It would be there. Here I'm defining a method called diameter. It's got this parameter there, but again, we don't really use it. It's just there for a reference to itself. So how to get the diameter? Well, just return 2 times this instance's radius. Cool. Here's a few more methods that are added. And then, of course, I can call them easy peasy. And then here's some simple tests, but we were talking at the end of last time. And by the way, for like the 2/3 of you that I don't really recognize right now, if you're saying, why is it going so fast? This was review of what we did last week. That's why I'm going fast. we kind of briefly talked at the end of the lecture how, these assert tests are getting kind of, they're doing the trick, but they're getting kind of harder to work with because there's so many of them. There's some setup required. I needed to make instances of circles, which, they're becoming a little less, they're becoming a little unwieldy. There's nothing wrong with them. They're doing the trick, but they're a little harder to manage. Okay, any questions before we jump on to the next one? Now, the next one is more of the same. We're just going to make the object that we're dealing with slightly more complex, but it's really the same underlying principles are there. So when we saw the circle class, we learned how to create a class, like how to write our own. We learned about the constructor, we learned about attributes and how to access them and modify them, although often we don't really like to modify the attributes associated with objects, because that makes the objects mutable, which might be fine, but sometimes we like to leave them alone because, immutableness is better. We learned about the functionality. We call them methods. We know how to write them. We know how to access them. And we also saw how to make actual instances of the circle class. We saw how to make objects, like circle objects. But in this topic, we're going to make another relatively simple class. It's going to be a sphere class. But there's going to be a little bit more complexity involved than the circle. And hopefully, this topic will make it a little more obvious how making objects kind of helps facilitate abstraction. Obviously, when I say abstraction, this isn't a new topic, right? We've been talking about abstraction in the context of writing functions the whole time, right? Every time you write a function, you're facilitating abstraction, right? You don't have to write every line of code in there. You just say, go turn on the car, instead of every instruction on how to turn on the car. Well, objects are just another layer of that. It's like a grouping of functionality and data that helps create another layer of abstraction. So the big things here is we're going to see a couple more of those magic methods, those dunder methods. And we're also going to see how objects can interact with one another to facilitate abstraction really easily. So we're going to create a sphere class. Like the circle class, the sphere is going to know its radius. Because with a radius, we know a lot about a sphere, right? We know its diameter, we know its surface area, we know its volume, right? But I am also going to keep track of, I'm going to say, okay, these spheres exist in a three-dimensional space. And the spheres are not only going to know their radius, but I want them to know their x, y, and z coordinate. So each sphere is going to have 4 attributes: x, y, z, and its radius. And with this, we can ask questions like, okay, how far apart are these spheres? Are these spheres overlapping? Are they touching? Whatever, right? So that's what we're going to do here. So, yeah, in order to find a sphere, we need to know its radius. With its radius, we know its diameter, surface area, volume. But yeah, we want to know its x, y, z coordinates. Yeah, there's nothing. Now, I've said, okay, I want to be able to calculate a sphere's diameter, surface area, volume. I want to know if 2 spheres are touching, if they're overlapping, how far apart are their edges, how far apart are their centers, etc. There's nothing stopping me from adding more functionality. I could add more and more and more until I'm satisfied with what my object is. But for our purposes here, I think this will be sufficient. But if at any point you're thinking like, okay, so it's important that he added that functionality. Well, no, not intrinsically important. It's just I've decided I'm writing these methods for my class. Don't think that it's necessary to be sufficient to write these ones for a specific object. It's just I'm just writing these ones because I'm writing these ones, just to show you. That's all. All right, so I'm just going to copy this. And here is the sphere class. I'm going to get rid of the docstring for brevity. We're importing math because we're going to want like pi, right? All I have here is I say, okay, class sphere is the name of the object. And then I've got my constructor or initializer. And you'll see the 4 parameters there. But of course, there's really 5. But remember, we kind of ignore self. We use it, but we don't provide any argument for this parameter when calling anything for the object. So self, it's a reference variable to refer to the current object. It takes its x, y, z, and a radius. So it takes its x, and it associates it with x. But you'll notice this x is just a parameter. It's just a variable that's contained within this method, within this constructor here. As soon as this constructor is done running, the variable x disappears. But self.x is entirely independent from x. Sure, they have the same value as a consequence of line 6 right here, but they are not connected in any way. In fact, the fact that this is called x is arbitrary. This will work just fine. I mean, it's a terrible parameter name because it has nothing to do with what it means. But don't think that, oh, it was called x, therefore the attribute should be called x. No, not at all. It's just good naming. Self.x is the x value. It's the attribute associated with the instance that's being created. Similarly with y, z, and radius. So, just as a refresher, I'm going to go down here. So remember, we don't give it anything for self. Even the little pop-up here. We'll put this at 0, 0, 0, 1, nope, 1, and b equal 10, 10, 10, 10. Now let's put this at 1, 1, 1, 1. Weird. So I've created 2 objects there. I have 2 spheres. They're both spheres, but they're different. They're separate. The first sphere, the one referenced by the variable a, what's its radius? If you think this is a trick question, you're in big trouble. This should be obvious. Everyone should be able to yell the answer out. 1, very good. B, what's B's radius? 10, perfect, great. Perfect. They both have a radius, but the values that they have are not related in any way. Everyone in here has a first name, but chances are most of you have different first names. You all have a first name, but they're different. So these spheres all have the attributes x, y, and z, and its radius, but the value of one has no bearing on the value of other as it stands. So if I were to say print a dot radius, well, it's 1. B's radius, it's 10. So at the end of the day, these attributes are just variables, but they're associated with a specific instance of an object. Any questions about this so far? This really is still more review from the last topic. So if you got a question, it's good to ask now before it gets more complex. Now let's add some methods. Well, let's start with these 3 right here. Diameter, surface area, and volume. Well, if I want to get a sphere's diameter, it's just return its 2 times its radius. If I want its surface area, well, it's 4 pi r squared. Why? Don't ask me. I had nothing to do with it. And volume, well, it's 4/3 pi r cubed. Great. That's it. If you're wondering, how did I know this? I don't remember, I looked it up. So when I run it, now remember, I had to run this code again to load up the new additions that I made to the class. And now here I can go down and ask, okay, B, what's your diameter? But this isn't an attribute, it's a method. So I have to add my parentheses. And what's its wrong? Oh, I got to recreate them. There. Its diameter is 20. What's its volume? It's that. I'm just going to trust it. So there we go. We added some methods. Again, notice these methods all seem to have one parameter, but that parameter really is the instance it's being called on. When I say b.volume, self and b are aliases. If I say a.volume, well, when this code gets run, a and self are aliases. There. On line 1 in that box, when it's run, the reference variable a and then the self-reference variable within the class are referencing the same object. On line 2, this reference variable b and then self within the class references the same object. This right here follows the same pattern we were following with the circle object. We just added, okay, we created our constructor. We added some parameters for the constructor or initializer. Within there, we had some attributes. The circle only had one attribute. This one has a few attributes, has 4. And we added some methods. With the circle, we had diameter, area, and perimeter. Perimeter? Was it whatever it was. And with the circle, or with the sphere, well, I've got diameter, surface area, and volume. So this right here isn't really anything crazy new. The newest thing here is the fact that I have 3 more attributes for the object. But it's just its x, y, z coordinate, right? It's a point in 3-dimensional space. Cool. Any questions so far? So, let's write a method to calculate the distance between 2 spheres' centers. Let's do that. I'll get rid of the doc string. There. All I did was put this all on separate lines. You can do that. Python's happy. I put them on separate lines just to make it fit into the same, like so you could read it easy. Cool? So I added a new method. Distance between centers. This function has 2 parameters. One's the implicit argument, self. It's a reference variable to the current instance. And we got another one there called other. Now, the fact that it's called other is arbitrary. I could call it whatever I want. But I've got another one called other. And this function, or pardon me, method, returns a float. But you'll notice the type hint has quotes around it. And this is required. This is just a type hint thing. This is because we're currently defining the type sphere. So it gets kind of weirded out. If you just put it in as a string, it just means like, okay, Python, just, it's the sphere. You can do that. If you put it in quotes, it lets you type in whatever you want. It's a more general, whatever. Don't worry too much about it. It's just, it's inside quotes. in this particular situation. You'll have to do similar things if you're writing a method where the type of something is the same as the class you've got here. Cool? Cool. Now, how do we calculate the distance between 2 points in three-dimensional space? Well, it's Euclidean distance, but it's in three-dimensional space. So it's the difference of the x's, y's, and z's squared. Hold on. Just because the other section actually wasn't quite sure. Raise your hand if you totally, absolutely remember, yeah, Euclidean distance formula. Okay, all right, good. Raise your hand if you totally, absolutely remember the Pythagorean theorem, though, right? So you do know the Euclidean distance formula, you just know it by another name. Here's why. Let me explain to you. I have really bad news for you. You've all had really bad math teachers if you don't know this. And it's not your fault, it's their fault. This is what you call learning debt. When you have a bad teacher, but they're your friend, and then you get to a point where you're supposed to know something and you don't, but it's someone else's fault along the way. So it's not your fault, it's their fault. So let's say we got a triangle, right? Okay, let's say we've got a triangle, we've got 3 points. Right? And we've got right? So far so good. This shouldn't be spooking anybody. And we have C, A, and B, right? Yeah? Yeah? And of course, we all know this comes out to, I'm just going to do it like this. Whoa, apparently my computer can't handle paint. So we've got like C squared equals A squared plus B squared, right? Or, you know what, let's make it a little bit more Python-y, right? 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 Yeah, so far so good. Which, of course, is the same thing as this. C equals of A squared plus B squared, right? All I did is I square rooted both sides. So if you take the square root of something squared, well, it just cancels out the square. And the other side gets square rooted, right? Yeah? So far so good. Seriously, tell me if you don't follow. The whole point of what I'm doing is to tell off your old math teachers, to show you how they should have showed you this. You can all see this pretty good too? Yeah? Okay, so far so good. Now, of course, to be clear, when I'm talking about spheres, I'm doing it in three-dimensional space. Here I'm only talking 2 dimensions. It works the exact same way. You just add the additional dimension. Don't worry too much. All right, so let's say, in reality, what you have is, some coordinate system, right? And I gave you 2 points. Right? So the underscores are like, it's like x1, y1, x2, y2, right? Yeah? And you know what? for the fun of it, let's just add what this, these are the 2 points. Let me be clear about something here. These are the 2 points. Let's say these are the centers of 2 circles I want to know the distance between, right? This third point here doesn't really exist though. But we know what it is because it's, well, it's, this is like x2 and y1. Or really in theory, there's an identical point up here that's x1 and y2. Doesn't really matter. Right? You could take, I'll do it in gray. There's another point here, really. This point is right? And then we've got this magical imaginary point here that really is x2 y1. So far, so good? These are the points we really care about. And if I want to know the distance between 2 things, the shortest distance between them is a straight line. But here's the thing. I know I can calculate how far, like what's the difference between x2 and x1? Well, that's just x2 minus x1, right? And that'll give me the length of the side of this triangle. A equals x2 minus x1. B equals y2 minus y1, the length of this here. So I can calculate the sides of these 2 triangles and then determine the hypotenuse of that triangle, which is the shortest distance between 2 points. This triangle equation that you've all known since, I don't know, when did you learn that? I can't remember. It's been a while. You learn it at least in high school, maybe before, I don't know, right? It's the same as the Euclidean distance between points. It's literally the same thing. It really is. So now you should go to your high schools and go tell them how bad they are, because they should have let you know this. This, you know, I'm going to take a step back and say, jokes aside, this to me shows the underlying deficiencies of like high school math is when they're not showing you the interconnectedness and the intuition behind what the hell you're actually doing. I know you all learned the Euclidean distance in high school. I know you all would have learned that, the distance between 2 points. You definitely learned that in high school. But if they didn't show you why the Euclidean distance expression, that formula, is what it is, if they didn't show you why, if they didn't give you the intuition as to why, what the hell's wrong with them? So that's not your fault. That's their fault. They never showed you why. High school math tends to be taught in a way where it's like, here's some information that was handed down by the gods, just memorize it. When in reality, it was just some asshole figured it out a long time ago. And there was a reason, and there was an intuition, there was motivation, there was like an algorithmic process they followed to discover this thing. It's the same thing. But instead of teaching you where it came from, they just show you the end result, which of course, to me, it's a hell of a lot harder to remember the end result if I know how to get there, versus knowing how to get there. Cool. Anyways, back to spheres. So raise your hand if it wasn't entirely clear how it's the same thing as the triangle, because I kind of want to make sure this is clear, because this understanding this interconnectedness is really important, I think. You figure, let's really quickly do just an example. Let's say x1 equals 1, y1 equals, let's make it like 2 and 1. And then x2 equals, I don't know, what's that look like? If that's 2, 2, 4, 6, 7. And y2 is, if that's 1, 2, 3, 4. Right? So let's say that's what we've got here. Whoop. Right? So the length of this side here is 7 minus 2. It's 5. So here, a equals 5, right? Because if this is 7 on the x-axis, and this is 2, 7 minus 2 is 5. We agree? Yeah, cool. And now here, if this is 4, and this is 1, well, the difference there is 3. 3 units on the y-axis. So that would be b equals 3. Now you just throw it into that expression. So what's 25 plus 9 is 34. I don't know, what's the square root of 34? No one knows it off the top of their head? Come on. 5.83095189. That's the distance. That's the distance between those 2 points, which also happens to be the hypotenuse as defined by that triangle. Cool. All right. That's all that's happening here, but in 3 dimensions. You know how you did like a squared plus b squared? Well, if it was a 3rd dimensional, you would say c squared. It would be the difference in the x's squared plus the difference in the y squared plus the difference in the z squared, square rooted. If you had another dimension, if you had 4 dimensions, which of course I'm not going to try to plot, you just keep going, and that's fine. So there we go. Now this, getting back to the object stuff, now this is where maybe self becomes a little bit more obvious. First, let's call this method there. The distance between my 2 squares, or 2 spheres, is centers, as defined right there, is apparently 15.588457, whatever. Okay? Now I am asking A. I'm saying A, what is the distance between centers to B? If we go look at this code, self is A. Other is B. If I go and call this, like this immediately after, it's going to give me the exact same result. It doesn't really matter who you ask. It's like saying, hey, how far away are you from them? And then asking you, how far away are you from them? It should be the same distance, right? It doesn't really matter. But self will be whatever the implicit argument is. Other will be, well, the one that we give it. The other one, the parameter we gave it. So I need to ask a sphere, how far away are you from something, some other sphere? And of course, then if I ask, hey, A, how far away are you from A? Well, that should give me back a 0, thank God. Because self and other will be the exact same. A, self, and other will all be aliases for the exact same sphere object. Now, if I had B at the exact same location, it would also hopefully give me back a 0 as well. Let's do that. 1, 1, 1. Yeah, okay, good. Good. But hopefully this now makes self a little bit more obvious. If I asked you, how far away are you from them, and you're both sphere objects in three-dimensional space, you say, okay, well, what's my x and what's your x? Take the difference, square it. What's my y and your y? Take the difference, square it. Z, difference, square it. Add them all up, square root. So you have to ask yourself, what's my x and what's the other one's x? That's how it's going. This is the first example of us showing you how these objects of the same type are now interacting with one another. I now can just ask, two spheres know their points in three-dimensional space. Now, if I want to know how far apart they are, I don't need to go whip out this formula anymore. I can go back to forgetting the Euclidean distance expression, like formula. I don't care about it anymore. I just ask the circles. Hey, circle, how far away are you from that circle? Which is a hell of a lot easier than saying, okay, circle, what's your x, what's your y, what's your z, what's your x, what's your y, what's your z, do the distance, no. I write the function, the method once, and now the circles, I've abstracted all that work out. Now I just ask the circles to figure it out. Way easier. Yeah. And now here's another one. Distance between edges. Well, this might sound like it's going to be complex, but it's really not. Here's why. All I need to do is calculate the distance between the centers and then minus their, let me show you. If I've got two, imagine these are spheres. I know they're not, they're circles. And I know the distance between their centers is this. All I need to know is the radius, radiuses, whatever. R1, R2. I just take the total distance and then chop off their radii from the total distance. So if you thought, uh-oh, well, the good news is I already have a method to calculate the distance between centers. And I'm going to call it right here. But notice, if I want to call a method that belongs to, that's within the class, I need to use self. Realistically, I could have used other to use the others ones, but that's kind of weird. I say, okay, I'm going to ask myself to calculate the distance between the centers of me and other. And then we're going to take my radius and their radius and just chop those off the total distances, and we're good to go. So here, if we go, let's put this back at like 10, 10, 10, 10, B, did I not run it? Run. There we go. The distance between the centers is 15.588. The distance between the edges, well, that's 15 minus 10 minus 1. That gets me to the 4.588. Cool. Now, what do you think would happen if, like, maybe this was at like 3? Think about this for a moment. What would this mean? And here, let's make this a little smaller so it's maybe a little easier to kind of think about. What that means is that I have one circle like this at point 1, 1, 1 with the radius 1. Then I have another circle at point 3, 3, 3 with a radius 5. I don't know, maybe it looks something like that. What do you think the distance between edges is going to be here? This one's kind of weird. Let's see what happens. Yeah, distance between edges is negative. When would the distances between the edges be negative? What would that mean? Yeah, it sounds like, let's just think about this for a second. If I got one circle here, pretend this is a circle. There, that's not bad. And then I got this one here. Think about what's the distance between edges right now. Is it getting bigger or smaller? Bigger or smaller? Bigger or smaller? What do you think it is about right now? Close to, at least. And now what do you think it is? Negative. So if it's negative, what must that mean? They're overlapping, they're colliding, they're touching, whatever. So all I really need to know now, if I want to check like overlap, whoops. This ends up being a relatively simple method to write. I just check. Okay, I ask myself, well, how far away are our edges? And if the distance is less than or equal to 0, they overlap. I guess here, if the distance is 0 and they're touching, I'm saying they're overlapping. If you think like, no, they shouldn't be overlapping. It really should only be when it's less than 0. Okay, fine, I'm not going to argue with you. But for whatever reason, I did it like this. I'm saying if the distance between the edges is ever not positive, they're overlapping in some way. Cool. So that ends up being kind of simple. Any questions about that? So if I go down here and I make like think about what this code is doing. I made a list object. There's a list class written somewhere, and I made a list object. And I'm saving it with a reference variable called alist that gets me to it. And then when I print out that object, what do I see? Well, I see a nice view of that list. This should become like, at this stage, you should be like, yeah, that's obviously what I get. But who told Python that when you print out a list, that's how you should print it out? Someone had to write that code. You probably never had to think about that before because it was abstracted away from you, which is a good thing. But now we're writing our own objects. And if I go down here and I say, okay, print A, remember A is some circle up here. I get this main sphere object at OX7E9529CEE9B0. What the hell does that mean? Okay, print B. I mean, it's telling me like the memory location of where this thing is actually stored. Look at that, they're pretty close to each other. Look at that, cool. But as a human, if I'm dealing with sphere objects and I wanted to like, okay, let's print it out quickly to see like, is this sphere what I expect it to be? Because how many times have you been dealing with lists and you're like, is the contents of this list what I want? Let's print it out and double check. You do it and then you see and you're like, yes or no. Now I'm playing around, I'm dicking around with some spheres and I want to check, do they look, like how do they look? Do they look like what I want? Let's print it out. Object at OX7 blah, 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 blah. Not very helpful, is it? It turns out that every class you write, you get a couple of methods for free, whether you write them or not. They're there. Remember how similar-ish, how like, you know how if you don't write a return, it's there? Python goes and adds like return none. This really isn't the same, but you know, we can kind of take that idea to be like, even though we didn't write a couple of methods, Python adds them there for us. And when I printed out A, Python called one of those methods that we got for free for us. The free one it gave us is called like repr. It's a magic method, a dunder one, the double underscore, the underscore underscore repr underscore underscore. That gets called automatically when you print something out. The default behavior, the one it gives you for free, just says, basically, tell me the name of the object and tell me where it is in RAM. And that's what we get. I didn't write it, someone else did, but I got it for free, and it was my class got it for free. But I'm looking at that, and I'm going to go, that's not that helpful to me. So instead what we do is we override that method we got for free. We write our own repr. That basically tells Python, ignore the one I got for free, use this one instead. And that lets us define, well, how do you want, if I print out a sphere object, what do you want it to look like? And that's where we'll go tomorrow or whenever we, no. Do we have class tomorrow? Wednesday, so we'll see this on Friday. Because Wednesday is the test. Now remember, I don't have office hour, or I don't have student hours today, but remember, if you need help, questions, thoughts, whatever, come to student hours, of course.